Welcome to the Big Pendulum at the Houston Museum of Natural Science, which I strongly recommend if you're ever in Houston. Here it is. It's a very large, massive bob hanging from a very long cable several stories up in the ceiling. The long cable gives it a very slow motion, nice hypnotic back and forth. It's so big, it actually acts as a Foucault pendulum. It's so big that you can sit here and watch the plane of the motion turn as the Earth rotates beneath the pendulum. That's why they set up these little pegs. So throughout the day, the bob knocks the pegs over. And I guarantee you, when a peg gets knocked over, sometimes the room erupts in cheers, but at the very least, one person goes, yes, every time. I'm actually not here to tell you, though, about the Foucault part of the pendulum. I want to think about the pendulum in terms of what we've learned in the class. So when we talked about real oscillators, we realized that most systems aren't as simple as the equations we use to describe them, right? Most oscillators are not linear. For the pendulum, it's linear as long as the amplitude is small. Well, here the amplitude really isn't small. In this case, its amplitude is over a meter. The height, the length of the cable is probably 20 meters. So we're looking at about a 10%. The amplitude is about 10% the length of the cable, which is really not that small of an angle. But we still use a small angle approximation probably if we were going to do a calculation. Another aspect that deviates from reality is that it goes all day. We talked about friction and damping in an oscillator. This thing certainly has damping in it. Up in the clamping mechanism, some friction will be generated. Even if you remove that, there's wind resistance for the bob moving back and forth. So it definitely would be damped. It should not go all day, but it does, which means it must be driven. So if up there in the roof, there's something driving it, we learned for a driven oscillator, if it's driven at a certain frequency, it'll move at that frequency. Right? There might be a transient, but eventually it moves at the frequency at which it's driven. Well, that means it may not be moving at its natural frequency. It's moving at its drive frequency. Who knows? Actually, no. It's not being driven that way. It's something called a parametric drive. The way it's being driven is that it moves, and when it's at a certain point of the motion, the bottom, it closes a contact and it gets a little magnetic push. And then when it goes through the bottom again, it gets another push. So it's not a continuous sinusoidal drive. It's this drive that depends on the motion itself. And in that case, it does oscillate pretty much at its natural frequency. So as you can see, even something as simple looking as a pendulum, many, many physical things are often going on, but then it approximately behaves as the simple systems we always talk about.